Hello, in this lecture we'll answer two questions. In the first question, we'll find out the length of line segment DE that is equal to x. In the second question, we'll find out the value of the shaded area that is inside this quarter circle. So we'll start with the first question. In the drawing, we have triangle ABC. We know that side angle ABC, this angle equals to 30 degrees. Angle ACB, this angle also equals to 30 degrees. We also know that angle DAE, this angle equals to 60 degrees. Line segment BD equals to 5 units. Line segment EC equals to 4 units, and our mission is to find out the length of line segment DE that is equal to x. Okay, so first of all, here we will focus on triangle ABC. So actually, in triangle ABC, we know that those two angles are equal to each other, they are both equal to 30 degrees. So we write it down. So in triangle ABC, we know that this angle, that is actually angle ABC, is equal to this angle, that is angle ACB, and both angles are equal to 30 degrees, therefore they are equal to each other. I will repeat again. In triangle ABC, angle ABC equals to angle ACB, and both angles are equal to 30 degrees, therefore they are equal to each other. And according to the rule that in front of equal angles in the triangle there are equal sides, we get that in front of this angle we have side AB, in front of this angle we have side AC, and according to the rule that I mentioned, side AB must be equal to side AC. Okay, so here side AB equals to side AC. So here side AB equals to side AC. In the next step, we define angle ABD, this angle as alpha, and we define angle EAC, this angle as beta, and we also know that the sum of the angles in any triangle is equal to 180 degrees, and especially in triangle ABC. So each angle we have a triangle ABC. We have this angle that is equal to 30 degrees, plus this angle that is also equal to 30 degrees, plus this angle that is equal to alpha according to our definition, plus this angle that is equal to 60 degrees according to what is given as the question, plus this angle that is equal to beta according to our definition. So in total, the sum of those all angles must be equal to 180 degrees. Here, this equation states that the sum of the angles in triangle ABC equals to 180 degrees. So here we have, in this side of the equation, we have 30 degrees plus 30 degrees is 60 degrees, and 60 degrees plus 60 degrees is 120 degrees, plus alpha plus beta equals to 180 degrees. So here we subtract 120 degrees from this equation, and we get that alpha plus beta equals to 180 degrees minus 120 degrees is 60 degrees. Okay, so actually found out that alpha plus beta equals to 60 degrees. In the next step, we'll do two constructions. In the first construction, from point A, we'll draw a straight line in such a way that the angle between the straight line and side AC will be equal to alpha. I'll repeat again. The angle between the straight line and side AC equals to alpha according to our construction. And the second construction that we will do is from point C we will draw a straight line in such a way that the angle between the straight line and side CA will be equal to 30 degrees. So the angle between this straight line and side AC equals to 30 degrees, also according to our construction. In the next step, we will extend this straight line and the other straight line by straight line until they intersect, until the two straight lines intersect with each other. And we will define the intersection point of the two straight lines as point F. I'll repeat again that this angle equals to alpha and this angle equals to 30 degrees according to our construction. So in the next step, we will prove that the new triangle that we built here, triangle AFC, is congruent to this triangle, triangle ABD. So I'll write it down. We prove the triangle ABD, this triangle, is congruent to this triangle, triangle AFC. So why those two triangles can go into each other? First of all, those two angles, they are both equal to alpha, therefore they are equal to each other. So I write it down. Angle BAD, this angle, is equal to this angle, it is actually angle CAF. And both angles are equal to alpha, therefore they are equal to each other. I'll repeat again. Angle BAD equals to angle CAF, and both angles are equal to alpha, therefore they are equal to each other. In addition, we have already found out that side AB equals to side AC. Okay? Side AB equals to side AC. And finally, those two angles, they are both equal to 30 degrees, therefore they are equal to each other. So this angle ABD is equal to this angle that is actually angle ACF, and both angles are equal to 30 degrees, therefore they are equal to each other. I repeat again, angle ABD equals to angle ACF, and both angles are equal to 30 degrees, therefore they are equal to each other. So we actually proved that this triangle ABD congruent. This is the sign of congruent to triangle AFC. According to angle side angle rule. Okay, I'll explain what I mean. We actually proved that those two angles alpha and 30 degrees and the side that attached to those two angles, that is side AB in triangle ABD, are corresponding congruent to those two angles that are alpha and 30 degrees and the side that attached to those two angles, that is side AC in triangle AFC. Therefore we actually proved that those two triangles can go into each other according to angle side angle rule. And from the fact that those two triangles can go into each other, we conclude two things. The first thing that we will conclude is that side BD equals to side FC. BD equals to FC. Side BD equals to side FC according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding sides, that is to say BD and FC, must be also equal to each other. But according to what is given us in the question, side BD equals to 5 units. So I can write here that BD equals to 5 units, and from this equation 5 equals to BD equals to FC, we will derive that side FC is also equal to 5 units. Okay, side FC equals to 5 units. And the second thing that we will conclude from the fact that those two triangles can go into each other is that side AD equals to side AF. Side AD equals to side AF. Repeat again, side AD equals to side AF. So according to the same rule that corresponding sides and congruent triangles are equal to each other, and if we define side AD as A, here side AD equals to A according to our definition, side AD equals to A, then from this equation A equals to AD equals to AF, we will derive that side AF is also equals to A. Side AF is also equals to A, so I can write here that side AF equals to A. In the next step, we'll join points E and F together by a straight line. So here by joining points E and F together by a straight line, we create a triangle EAF. So we prove the triangle ADE, the green triangle, is congruent to the triangle that we created, the orange triangle, triangle AEF. So here we have already proved that alpha plus beta equals to 60 degrees. So here this angle EAF that is equal to alpha plus beta, it is equal to 60 degrees according to what we have already proved. So I've already mentioned, we prove that the green triangle ADE, is congruent to the orange triangle EAF. So, why those two triangles congruent to each other? First of all, we just right now proved that side AD equals to side AF, and both sides are equal to A, therefore they are equal to each other. So here, side AD equals to side AF, and they are both equal to A. And put again, side AD equals to side AF, and they are both equal to A, therefore they are equal to each other. In addition, those two angles, they are both equal to 60 degrees, therefore they are equal to each other. So here actually this angle, that is actually angle DAE, is equal to this angle, that is actually angle EAF. And both angles are equal to 60 degrees, therefore they are equal to each other. And repeat again. Angle DAE in the green triangle is equal to angle EAF in the orange triangle. Both angles are equal to 60 degrees, therefore they are equal to each other. And finally, this side AE, is a common side that belongs to both triangles. So I can write down that side AE equals to itself. AE equals to AE is the common side that belongs to both triangles. I'll repeat again. Side AE equals to side AE. It is a common side that belongs to both triangles. Okay, so actually we proved that the green triangle ADE, is congruent to the orange triangle AEF, according to side angle side rule. Repeat again, triangle ADE congruent to triangle AEF according to side angle side rule. So I'll explain what I mean. We actually proved that those two sides and the angle that is between them in the green triangle congruent to those two sides, and the angle that is located between those two sides in the orange triangle. Therefore, we prove that those two triangles can go into each other according to side angle side rule. And from the fact that those two triangles can go into each other, we conclude that side DE equals to side EF. So, write it down, side DE equals to side EF. I'll repeat again. From the fact that the green triangles can go into the orange triangle, we conclude that side DE equals to side EF according to the same rule that the corresponding sides of congruent triangles are equal to each other. But according to what is given on the question, side DE equals to x. So I can write here that DE equals to x, DE equals to x, and from this equation x equals to DE equals to EF, we will derive that side EF is also equals to x. Okay, side EF is also equals to x. In the next step, I will present to you the law of cosines, and we will implement the law of cosines in this triangle, triangle EFC. Okay, so what is the law of cosines? The law of cosines is true in any triangle. So you can write down that in any triangle, so here, this triangle ABC, could be any triangle, and we know that side AB equals to A units in its length, side AC equals to B units in its length, and the angle between side AB and side AC is theta, and side BC equals to C units in its length, then in this triangle ABC, the following equation is true, that C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. I'll repeat again, in this triangle ABC, that could be any triangle, C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. So we will implement the law of cosines in this triangle EFC. So I'll copy triangle EFC in this page and we'll implement the law of cosines in triangle EFC. Angle ECF, this angle equals to 30 degrees plus 30 degrees, that is 60 degrees. Side FC equals to 5 units in its length. Side EC equals to 4 units in its length, according to what is given in the question. And we just right now found out that side EF equals to X units in its length. So this is triangle EFC that they copied from the original drawing. So we'll implement the law of cosines in this triangle, triangle EFC. So according to the law of cosines, we get that in triangle EFC, the following equation is true, that x squared equals to 4 squared plus 5 squared minus 2 times 4 times 5 times cosine 60 degrees. So this equation is the implementation of the law of cosines in triangle EFC. I repeat again, in triangle EFC, the following equation is true, that x squared equals to 4 squared plus 5 squared minus 2 times 4 times 5 times cosine 60 degrees according to the law of cosines. Okay, so actually I found out that x squared equals to 4 squared, that is 16, plus 5 squared, that is 25, minus 2 times 4 is minus 8, and minus 8 times minus 5 is minus 40, and cosine 60 degrees equals to 1/2, so we substitute cosine 60 degrees by 1/2. So actually this expression in total equals to minus 40 times 1/2. So we actually found that x squared equals to 16 plus 25 is 41, minus 40 over 2 is minus 20. So in conclusion, we found out that x squared equals to 41 minus 20. So x squared equals to 41 minus 20 is 21. So we found out that x squared equals to 21. So here we take a root out of this equation and we get that x equals to the positive square root of 21. Why it is the positive square root? Because of the fact that x is a length, and as a length it must be a positive number. So either x equals to the positive square root of 21, or in terms of numbers it is equal to 4.58 units. Okay. I repeat again, I found out that line segment DE that is equal to x, it is equal to either the positive square root of 21, or in terms of numbers it is equal to 4.58 units. Okay, we finished with the first question. In the next step I will present to you the second question. Okay. In the drawing, we have a quarter circle. Inside this quarter circle, we have a circle and a semicircle that are tangent to each other at this point. And we also know that this circle is tangent to the quarter circle at this point. And our mission was to find out the value of the shaded area. So first of all, because of the fact that this is a quarter circle, therefore this point must be the center of the quarter circle. So we define This point is point O, so I write it down that point O is the center of the quarter circle. Okay, point O is the center of the quarter circle. In addition, this angle must be equal to 90 degrees. This angle equals to 90 degrees. We define this point as point A. Here, OA is the radius of the quarter circle. We define this point as point B. And BO is also the radius of this quarter circle. Those things are true in any quarter circle. Okay, we can write down here that AO and BO are on the eye of the quarter circle. Okay. In the next step, we will define the point of tendency of tangent AO with this circle as M. I repeat again that point M is the point of tangency of tangent OA with this circle. I forgot to mention that the radius of this circle is equal to 2 units according to what is given as the question, and the radius of the semicircle is also equal to 2 units according to what is given as the question. We will define the center of this circle as point P, and we will define the center of this semicircle as point Q. Point P is the center of the circle, point M is the point of the circle itself, therefore line segment PM is the radius of this circle, and we actually have here rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So here tangent AB is tangent to this circle at point M. Point M is the point of tendency. And we have here the radius OM that is drawn to the point of tendency. Whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. So if AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule number 1. We can implement rule number 1 in our drawing. Why? Because in our drawing we have here the radius PM that is drawn to the point of tendency. That is to say, it is drawn to point M. That is the point of tendency of tangent OA with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent OA will be perpendicular to the radius MP. So if OA is perpendicular to MP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. So from the center of this circle that is point P, we will draw perpendicular on QO. Okay, here. So actually, this angle equals to 90 degrees according to our construction, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point P and QO as L. L is the touching point of the perpendicular from point P and QO. So we actually created here quadrilateral LPOM, and inside quadrilateral LPOM we have 1, 2, 3 right angles. Okay, and the sum of 3 right angles is 90 times 3 is 270 degrees, plus the size of the fourth angle, that is actually angle LPM. In total, the sum of those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Okay, so here we subtract 270 degrees from this equation, and we get that the missing angle LPM, equals to 360 degrees minus 270 degrees, it is equal to 90 degrees. So angle LPM, it is a right angle, it is equal to 90 degrees, so we can write here that this angle equals to 90 degrees. So actually we found out that all the angles inside quadrilateral LPOM are right angles, and any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we will relate to quadrilateral LPOM as a rectangle. Okay, quadrilateral LPOM is a rectangle. Why? Because it has 4 right angles. Okay. And we also know that the opposite sides of a rectangle are equal to each other. So the opposite sides of rectangle LPOM, they are equal to each other. So it means that side PM must be equal to side LO. Side PM equals to side LO according to the rule that the opposite sides of a rectangle are equal to each other. Okay, but we know that PM equals to 2 units, so we can write here that PM equals to 2, and from this equation 2 equals to PM equals to LO, we will derive that LO, that side LO is also equals to 2 units. Okay, we can write here that side LO equals to 2 units. Likewise, according to the same rule, that the opposite sides of rectangle are equal to each other, we will get that side LP must be equal to side OM. LP equals to OM. Side LP equals to side OM according to the same rule. So if we define side LP as X, here the side LP equals to X according to our definition, Then from this equation x equals to LP equals to OM, we will derive that side OM is also equals to x. Here, side OM equals to x. In the next step, we'll focus at this point, that is the touching point of the circle with the quarter circle. So we will define the touching point of the quarter circle and the circle as point Z. So actually those two circular shapes have an internal knot between them at point Z. That is to say, they are touching each other internally at point Z. Z is the touching point of the quarter circle with the circle. And whenever we have an internal notch between two circular shapes, then the straight line that connects their centers together must pass through their touching points. Okay, so here point O is the center of the quarter circle. Point P is the center of the circle. And the straight line that connects, the straight line that joins their centers together is the straight line OP. So according to the rule that I mentioned, the straight line OP this straight line OP must pass through point Z, that is their touching point. Okay, the straight line OP must pass through their touching point, that is point Z. That is to say, line segment OPZ is one straight line. So you can write down here that line segment OPZ is one straight line. So if line segment OPZ is one straight line, you can also express it that points O, P, and Z, those 3 points, they are all located on the same straight line. Okay, it is exactly like saying that OPZ is one straight line. So if line segment OPZ is a straight line, then OZ also must be a straight line. So here, line segment OZ is also a straight line. So you know that OZ is a straight line. We also know that point O is the center of the quarter circle. Point Z is the point of the quarter circle itself. Therefore, this is exactly the definition of a radius. That is to say, OZ is the radius of the quarter circle. So we can write down that the straight line OZ is the radius of the quarter circle. Okay, OZ is the radius of the quarter circle. So we will define the radius of the quarter circle as capital R. Therefore, OZ, the straight line OZ equals to capital R. It is the radius of the quarter circle. That is equal to capital R according to our definition. But we also know that point P is the center of the circle, point Z is a point on the circle itself, therefore PZ is the radius of this circle that is equal to 2 units according to what is given as the question. So here we can write down also that PZ equals to 2 units. It is the radius of the circle. So here we know that OZ equals to capital R, it is the radius of the quarter circle, and PZ equals to 2, it is the radius of the circle. And what is the length of line segment PO? From the drawing it is very easy to see that the length of this line segment PO equals to ZO minus ZP. Again, ZO minus ZP equals to PO. So I write it down. PO equals to ZO minus ZP. I repeat again, the length of line segment PO equals to ZO minus ZP. So PO equals to ZO or OZ, it is the same. So ZO is the radius of the quarter circle that is equal to capital R according to our definition, while ZP, it is PZ of course. So PZ that is equal to ZP, it is equal to 2 units, it is the radius of the circle. So in conclusion, we found out that PZ equals to capital R minus 2. PO equals to capital R minus 2. Okay, here the length of line segment PO or OP is equal to capital R minus 2. In the next step, I will copy the right triangle POM in a new page and will implement the Pythagoras theorem on this right triangle POM. Okay? Side OM equals to x units. PM is the radius of the circle that is equal to 2 units. And you just write down found out that the hypotenuse PO or OP equals to capital R minus 2 units in its length. So this is the right triangle OPM that I copied from the original drawing. So here, according to the Pythagoras theorem, here my PT is abbreviation for Pythagoras theorem. So according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, the square of the hypotenuse is OP squared, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to OM squared plus PM squared. So I repeat again that according to the Pythagoras theorem and equation number 1, OP squared equals to OM squared plus PM squared. Okay, so OP equals to capital R minus 2, so OP squared is capital R minus 2 squared. And it is equal to OM squared. OM equals to X, so OM squared equals to X squared plus PM squared. PM equals to 2, so PM squared is 2 squared, that is 4. So according to equation number 1, we found out that R minus 2 squared equals to X squared plus 4. Here we open the brackets on this side of equation number 1 and we get that according to equation number 1, R minus 2 squared equals to R squared plus 2 squared, that is 4, minus 2 times R times 2 is minus 4R, and it is equal to X squared plus 4. So here we have 4 on both sides of the equation number 1, so 4 will get cancelled. So what is left from equation number 1 after I cancelled 4? What is left? It is actually, here we have R squared minus 4R, that is equal to X squared. So according to equation number 1, I found out that X squared equals to R squared minus 4R. Okay? So, in the next step, we focus at this point, that is the touching point between the circle and the semicircle, and we will define this touching point as point T. So actually, those two circular shapes, that is to say the circle and the semicircle, have an external notch between them at point T. That is to say they are touching each other externally at point T. And whenever you have an external notch between two circular shapes, then the straight line that joins their centers together must pass for their touching point. Okay, I repeat again, whenever you have an external notch between two circular shapes, then the straight line that connects their centers together must pass for their touching point. Here, point P is the center of the circle, point Q is the center of the semicircle, and the straight line that connects their centers together is the straight line QP, and that straight line QP, according to the rule that I mentioned, must pass for their touching point, that is actually point P. So here we get here that actually that line segment QTP is one straight line. So can I know that line segment QTP is one straight line or we can also express the same idea that the 3 points Q, T, and P, they are all located on the same straight line. It is exactly like saying that QTP is one straight line. So if QTP is one straight line, then QP also is a straight line. So I can write down that QP is a straight line. QP is a straight line. So here point Q is the center of the semicircle. Point T is the point on the semicircle itself. That is to say, QT is the radius of the semicircle. That is equal to 2 units according to what is given as the question. Likewise here, point P is the center of the circle. Point T is the point on the circle itself. That is to say, TP is the radius of this circle that is also equal to 2 units according to what is given as the question. And what is the length of QP? The length of the straight line QP here from the drawing, it is very easy to see that the length of the straight line QP equals to QT plus TP. I repeat again, the length of the straight line QP equals to QT plus TP. So here QP equals to QT is 2 plus TP is 2. In conclusion, I found out that QP equals to 2 plus 2, that is 4. So I found out that QP equals to 4 units. Here, point Q is the center of the semicircle. Point B is the point on the semicircle itself. This is exactly the definition of a radius. That is to say, BQ is the radius of this semicircle that is equal to 2 units. Okay? And what is the length of line segment QL? The length of line segment QL from the drawing, it is very easy to see that QL equals to BO, that is the radius of the quarter circle, minus BQ, that is the radius of the circle, minus LQ. It is equal to 2 units. So in conclusion, we found out that the length of line segment QL equals to BO minus BQ minus LQ. So the length of line segment QL is equal to BO, as I already mentioned, here BO is the radius of the quarter circle that is equal to capital R according to our definition, minus BQ is equal to 2 units, minus LO that is also equal to 2 units. So in conclusion, we found out that QL equals to capital R minus 2, capital R minus 2 equals to capital R minus 4. So in conclusion, we found out that QL equals to capital R minus 4. So we can write down here that QL equals to capital R minus 4. So in the next step, we will implement the Pythagoras theorem on the right triangle, triangle QLP. So I'll copy the right triangle QLP in a new page and we'll implement the Pythagoras theorem on this triangle QLP. Okay. So we just find out that QL equals to capital R minus 4. This angle equals to 90 degrees according to our construction, angle QLP. LP equals to X. And the hypotenuse QP, we have already found out that the hypotenuse QP equals to 4 units, it is actually 2 plus 2. Okay, so this is the right triangle QLP that I copied from the original drawing. So here we implement the Pythagoras theorem. By PT is the abbreviation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. This will be equation number 2. So the square of the hypotenuse is QP squared, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to QL squared plus LP squared. Repeat again, according to the Pythagoras theorem, QP squared equals to QL squared plus LP squared. So QP equals to 4, therefore QP squared is 4 squared, that is 16. That is equal to QL squared. QL equals to capital R minus 4, therefore QL squared equals to capital R minus 4 squared plus LP squared. LP equals to X, so LP squared equals to X squared. So here we'll open the brackets on this side of equation number 2 and we'll get that 16 equals to R minus 4 squared equals to R squared plus 4 squared, that is 16, minus 2 times R times 4 is minus 8R, plus X squared. So here we have 16 on both sides of equation number 2, so 16 will get cancelled. And what is left from equation number 2 after we cancel 16? In this side of the equation, nothing is left, so we have 0. That is equal to R squared minus 8R plus X squared. So here we will add 8R to this equation, equation number 2, and we'll get that according to equation number 2, 0 plus 8R is 8R. That is equal to R squared plus X squared. So here we subtract R squared from this equation, equation number 2, and we get that according to equation number 2, eight R minus R squared equals to X squared. So actually we have here second expression for X squared. X squared equals to 8R minus R squared according to equation number 2, while we have already found out that according to equation number 1, R squared minus 4R equals to x squared. So actually we have here two different expressions for x squared. Therefore, we create the third equation, equation number 3, that states that x squared, according to equation number 1, must be equal to x squared according to equation number 2. So here, x squared according to equation number 1 equals to r squared minus 4r. And it must be equal to x squared according to equation number 2, that is equal to 8r minus r squared. So in conclusion, we found out that according to equation number 3, r squared minus 4r equals to 8r minus r squared. Here we will add r squared to this equation, equation number 3, and we get that according to equation number 3, r squared plus r squared is 2r squared minus 4r equals to 8r. Here we will add 4r to this equation, equation number 3, and we get that 2r squared minus 4r plus 4r is 0, that is equals to 8r plus 4r is 12r. So in conclusion, we found out that according to equation number 3, 2r squared equals to 12r. Here we will divide this equation, equation number 3, by 2, and we get that according to equation number 3, two r squared over 2 is r squared. That is equal to 12r over 2 is 6r. So in conclusion, we found out that according to equation number 3, r squared equals to 6r. Here we subtract 6r from this equation, equation number 3, and we get that according to equation number 3, r squared minus 6r equals to 0. So here we take r as a common factor from this expression. So r is a common factor. What is left from r squared after we took from it r as a common factor? What is left? It is actually r. And what is left from minus 6r after we took from it r as a common factor? What is left? It is actually 6. So in conclusion, we found out that r times r minus 6 equals to 0. So here we will have two solutions that are possible for r. The first solution for r is that r equals to 0. But because of the fact that r is the radius of this quarter circle, is the length, it must be a positive number, it can never be equal to 0, so we cancel this solution, and we left only with the second solution, that r minus 6 equals to 0. Here we add 6 to this equation, and we get that r equals to 6. So we found out that the radius of this quarter circle is equal to 6 units. Therefore, we know that the area of any quarter circle equals to the area of the circle over 4. That is to say, it must be equal to pi r squared over 4. And r equals to 6. Okay? And what is the value of the shaded area? The value of the shaded area it is very easy to see from the drawing that the value of the shaded area equals to the area of the quarter circle minus the area of the circle minus the area of the semicircle. I'll repeat again. The value of the shaded area equals to the area of the quarter circle minus the area of the circle minus the area of the semicircle. So the value of the shaded area equals to the area of the quarter circle, and I've already mentioned that the area of the quarter circle equals to pi r squared over 4, r equals to 6, minus the area of the circle. The area of the circle equals to pi r squared and r equals to 2, so it is pi 2 squared. Minus the area of the semicircle. The area of the semicircle is pi r, the area of the circle over 2, that is pi r squared over 2, and r equals to 2, so it is pi 2 squared over 2. So, in conclusion, we found out that the value of the shaded area equals to pi r squared over 4, that is the area of the circle, minus pi 2 squared, that is the area of the circle, minus pi 2 squared over 2, that is the area of the semicircle. Here we found out that capital R equals to 6, so, and therefore capital R squared is 6 squared, that is 36. So in total, this expression equals to 36 pi over 4. This is the area of the quarter circle minus pi 2 squared. 2 squared is 4, and 4 times pi is 4 pi. Minus pi 2 squared over 2. 2 squared is 4, and 4 over 2 is 2, so it is 2 times pi. This expression equals to 2 pi in total. Okay, so found out that the value of the shaded area equals to 36 pi over 4 minus 4 pi minus 2 pi. 36 over 4 is 9. So in total, this expression equals to 9 pi. That is the area of the quarter circle minus the area of the circle, that is 4 pi, minus the area of the quarter circle, that is 2 pi. Here, 9 pi minus 4 pi is 5 pi, and 5 pi minus 2 pi is 3 pi. So actually we found out that the value of the shaded area equals to either 3 pi square units, or in terms of numbers it is equal to 9.42 square units. Okay, I'll repeat again. The value of this shaded area equals to either 3 pi square units, or in terms of numbers it is equal to 9.42 square units. Okay, we finished with the second question. In the next step I will summarize the lecture. We start with the first question. So, in the drawing we have triangle ABC. Angle ABC equals to 30 degrees. Angle ACB also equals to 30 degrees. Line segment BD equals to 5 units. Line segment EC equals to 4 units. And our mission is to find out the length of line segment DE, that is equal to X. Okay, so first of all we focused on triangle ABC. This triangle, in triangle ABC, those two angles are equal to each other, they are both equal to 30 degrees. So here, in triangle ABC, angle ABC equals to angle ACB, and they are both equal to 30 degrees, therefore they are equal to each other. And according to the rule that in front of equal angles in the triangle there are equal sides, you get that in front of this angle we have side AB, in front of this angle we have side AC, and according to the rule that I mentioned, those two sides must be equal to each other, that is to say, side AB equals to side AC. Then we define angle BAD as alpha, and we defined angle EAC as beta, and we also know that the sum of the angles in any triangle is equal to 180 degrees, and especially the sum of the angles in triangle ABC must be equal to 180 degrees. So each angle we have a triangle ABC, we have this angle equals to 30 degrees, plus this angle that is equal to 30 degrees, plus this angle that is equal to alpha, plus this angle that is equal to 60 degrees, plus this angle that is equal to beta. In total, the sum of those all angles, they must be equal to 180 degrees. Okay, 30 degrees plus 30 degrees plus alpha plus 60 degrees plus beta equals to 180 degrees. So 30 degrees plus 30 degrees is 60 degrees, and 60 degrees plus 60 degrees is 120 degrees. So in this side of the equation we have 120 degrees plus alpha plus beta, and it must be equal to 180 degrees. So here we subtracted 120 degrees from this equation, and we found out that alpha plus beta equals to 180 degrees plus 120 degrees is 60 degrees. So we found out that alpha plus beta equals to 60 degrees. Then we did a construction. We did two constructions actually. From point A, we drew a straight line in such a way that the angle between this straight line and side AC of triangle ABC equals to alpha. So this angle equals to alpha according to our construction. And the second construction that we did is that from point C, we drew a straight line in such a way that the angle between the straight line and side CA will be equal to 30 degrees. So this angle equals to 30 degrees, also according to our construction. Then we extended the two straight lines until they intersect with each other at point F. In this way we created triangle AFC, and we proved that triangle AFC is congruent to this triangle ABD. So why those two triangles can go into each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. Here, angle BAD equals to angle CAF equals to alpha. In addition, those two sides are equal to each other, that is to say side AB equals to side AC according to what we have already proved. Side AB equals to side AC, and finally those two angles, they are both equal to 30 degrees, therefore they are equal to each other. So here side ABD, angle ABD equals to angle ACF, they are both equal to 30 degrees, therefore they are equal to each other. So we actually proved that triangle ABD is congruent to triangle AFC according to angle side angle rule. We explain what I mean here. Those two angles and the side that is attached to those two angles, that is side AB and triangle ABD, are corresponding congruent to those two angles, and the side that attached to those two angles, that is actually side AC in triangle AFC. Therefore we proved that those two triangles can go into each other according to angle side angle rule. And from the fact that those two triangles can go into each other, we conclude two things. The first thing that we will conclude is that side BD equals to side FC. Here side BD equals to side FC, according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding sides, that is to say BD and FC, must be also equal to each other. But according to what is given us the question, side BD equals to 5 units. So we can write here that BD equals to 5, and from this equation 5 equals to BD equals to FC, we will derive that side FC is also equals to 5 units. Here, side FC equals to 5 units. And the second thing that we will conclude from the fact that those two triangles can go into each other is that side AD equals to side AF. Side AD equals to side AF, according to the same rule that corresponding sides in congruent triangles are equal to each other. And if we define side AD as A, here side AD equals to A according to our definition, then from this equation A equals to AD equals to AF, we will derive that side AF is also equals to A. Okay? Side AF also equals to A. Then we join points E and F together by straight line, and we proved that the green triangle is congruent to the orange triangle. Okay, so why those two triangles can go into each other? First of all, side AD equals to side AF, and both sides are equal to A, therefore they are equal to each other. Here, side AD equals to side AF equals to A. In addition, those two angles they are both equals to 60 degrees, therefore they are equal to each other. So here, angle DAE in the green triangle is equal to angle EAF in the orange triangle, and both angles are equal to 60 degrees, therefore they are equal to each other. And finally, side AE is a common side that belongs to both triangles, so this side is equal to itself. AE equals to AE is a common side that belongs to both triangles. So we actually proved that those two triangles can go into each other according to side angle side rule. We'll explain what I mean. Here, those two sides and the angle that is included between those two sides, that is to say this angle in the green triangle, can go into those two sides and the angle that is included between those two sides in the orange triangle. Therefore, those two triangles can go into each other according to side angle side rule. And from the fact that those two triangles can go into each other, we conclude that side DE in the green triangle equals to side EF in the orange triangle. DE equals to EF according to the rule, the same rule that corresponding sides in congruent triangles are equal to each other. But according to what is given as the question, side DE equals to X. Here we can write down that D equals to X, and from this equation X equals to DE equals to EF, we will derive that side EF is also equals to X. Here side EF equals to X. In the next step I presented to you the law of cosines, and we implemented the law of cosines in this triangle, triangle EFC. So what is the law of cosines? The law of cosines is true in any triangle. So this triangle, triangle ABC, could be any triangle. We know that side AB equals to A units in its length, side AC equals to B units in its length, and the angle between side AB and side AC is theta. And we also know that side BC equals to 3 units in its length. Then in this triangle, that could be any triangle, the following equation is true, that C c squared equals to a squared plus b squared minus 2 times a times b times cosine theta. I repeat again, c squared equals to a squared plus b squared minus 2 times a times b times cosine theta. Then we implemented the law of cosines in this triangle EFC. In triangle EFC, this angle ECF equals to 30 degrees plus 30 degrees, that is 60 degrees. So this angle equals to 60 degrees, side FC equals to 5 units, side EF equals to x, and side EC equals to 4 units. So we implemented the law of cosines in this triangle, and this angle ECF equals to 60 degrees. We implemented the law of cosines in this triangle ECF, and according to the law of cosines, we get that x squared equals to 4 squared plus 5 squared minus 2 times 4 times 5 times cosine 60 degrees. I repeat again, x squared equals to 4 squared plus 5 squared minus 2 times 4 times 5 times cosine 60 degrees. So here x squared equals to 4 squared is 16 plus 5 squared is 25 minus 2 times 4 is minus 8, and minus 8 times 5 is minus 40. And cosine 60 degrees is 1/2, so we substitute cosine 60 degrees by 1/2. So in total, this expression equals to minus 40 degrees times 1/2. So in conclusion, we found out that x squared equals to 16 plus 25 is 41, and minus 40 over 2 is minus 20. So in conclusion, we found out that x squared equals to 41 minus 20. So x squared equals to 41 minus 20, that is 21. Here we took a root out of this equation and we found out that x equals to either to the positive square root of 21, or in terms of numbers it is equal to 4.58 units. And the reason that x equals to only to the positive square root of 21 is because of the fact that x is a length. As a length, it must be a positive number. So in conclusion, we found out that the length of line segment D equals to either to the positive root of 21, or in terms of numbers, it is equal to 4.58 units. We finished the first question. Then I presented to you the second question. Here in the second question, we have in the drawing the quarter circle. This is a quarter circle. Inside the quarter circle, we have a circle and a semicircle that are tangent to each other at point T. And we also know that the circle is tangent to the quarter circle at point Z. Point Z is the touching point between the circle and the quarter circle. And we also know that the radius of the circle and also the radius of the semicircle, both radii are equal to 2 units. And our mission is to find out the value of the shaded area. So first of all, because of the fact that this is a quarter circle, then this point O must be the center of the quarter circle, and angle QOA must be equal to 90 degrees, and OA and also BO must be the radii of the quarter circle. Okay? So we have here the tangent OA is tangent to this circle at point M. Point M is the point of tendency. Point P is the center of the circle. Point M is the point of the circle itself. Therefore, PM is the radius of this circle that is equal to 2 units. And we also have rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So here we have the radius OM that is drawn to the point of tendency, that is to say, it is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. So if AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees. We implemented rule number 1 in our drawing. In our drawing, we have the radius PM that is drawn to the point of tendency. That is to say, it is drawn to point M, that is the point of tendency of tangent OA with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent OA will be perpendicular to the radius MP. So if OA is perpendicular to MP, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule number 1. Then, from the center of this circle, that is to say from point P, we draw perpendicular on QO. So this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. And we define the touching point of the perpendicular from point P and QO as L. Okay, so actually we created here quadrilateral LPOM that has 1, 2, 3 right angles. Repeat again, the quadrilateral LPOM, we have 3 right angles and the sum of 3 right angles is 90 times 3 is 270 degrees plus the size of the fourth angle that is actually angle LPM. In total they must be equal to 360 degrees. According to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Here we subtracted 270 degrees from this equation. We found out that the missing angle LPM equals to 360 degrees minus 270 degrees, it is equal to 90 degrees. So actually we found out that this angle is a right angle. Therefore inside quadrilateral LPOM we have 4 right angles, and any quadrilateral that has 4 right angles must be at least a rectangle if not a square, so we relate to quadrilateral LPOM as a rectangle, and we also know that the opposite sides of a rectangle are equal to each other. So the opposite sides of a rectangle LPOM must be equal to each other. That is to say, PM equals to LO. PM equals to LO according to the rule that the opposite sides of a rectangle are equal to each other. But we have already found out that PM equals to 2. We know that PM equals to 2, and from this equation 2 equals to PM equals to LO, we will derive that LO also equals to 2 units. Here LO equals to 2 units. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we get that LP equals to OM. LP equals to OM, and if we define LP as X, here LP equals to X according to our definition, then from this equation X equals to LP equals to OM, we will derive that OM is also equals to X. Here OM is also equals to X. Okay, then we focus, the next step we focused at point Z. Point Z is the point of tendency of the circle and the quarter circle, or the touching point of the quarter circle and the circle. And at point Z, the circle and the quarter circle have an internal lunge between them, that is to say they are touching each other internally at point Z. And we know that if we have two circular shapes that are touching each other internally, they have an internal lunge between them, then the straight line that joins their centers together must pass through their touching point. Okay, I repeat again, whenever you have two circular shapes with an internal lunge between them, then the straight line that joins their centers together must pass through their touching point. So here point O is the center of the quarter circle, point P is the center of the circle itself. Therefore, the straight line PO is the straight line that connects their centers together, and according to the rule that I mentioned, the straight line PO must pass from point Z. That is to say, ZPO is one straight line. Okay, here ZPO or OPZ, it is the same. OPZ is one straight line. Okay, so as I already mentioned before, you can also say that all 3 points that are Z, P, and O actually are located on the same straight line. It is exactly like saying that OPZ is one straight line. So if OPZ is one straight line, then OZ is also a straight line, and we know that point O is the center of the quarter circle. Point Z is the point on the circle itself. Therefore, the straight line OZ is the radius of the quarter circle, because this is exactly the definition of a radius. So here OZ is the radius of the quarter circle. So we define the radius of the quarter circle as capital R. So here OZ equals to capital R according to our definition. And we also know that P is the center of the circle. Z is the point of the circle itself. That is to say, PZ is the radius of the circle that is equal to 2 units according to what is given as the question. So in conclusion, we found out that PZ equals to 2 units, and OZ, that is the radius of the quarter circle, it is equal to capital R according to our definition. Okay, so and what is the length of line segment PO? From the domain, it is very easy to see that the length of line segment PO is equal to ZO minus PZ. Again, ZO minus PZ equals to PO. Here again, PO equals to ZO minus PZ or ZP. So PO equals to OZ. OZ equals to capital R. It is the radius of the quarter circle minus ZP. ZP equals to PZ, and it is equal to 2 units. It is the radius of the circle. So in conclusion, we found out that PO equals to capital R minus 2. Then I copied this triangle OPM in a new page, and we implemented the Pythagoras theorem on this triangle OPM. So this is the right triangle OPM that I copied from the original drawing. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the sides of the perpendiculars. The square of the hypotenuse is OP square, and it must be equal to the sum of the sides of the perpendiculars. That is to say, it must be equal to OM square plus PM square. So in conclusion, according to equation number 1 and Pythagoras theorem, OP square equals to OM square plus PM square. OP equals to capital R minus 2, therefore OP square is capital R minus 2 square. OM equals to X, therefore OM square is X square, plus PM square. PM equals to 2, so PM square is 2 square, that is 4. So in conclusion, according to equation number 1, we found out that R minus 2 square equals to X square plus 4. We open the brackets on this side of equation number 1, we found out that R minus 2 square equals to R square plus 2 square, that is 4, minus 2 times R times 2, that is minus 4R, and it is equal to X square plus 4. Here we have 4 on both sides of the equation number 1, so 4 will get cancelled, and what is left from equation number 1 after we cancel 4? What is left is actually in this side of the equation we have R square minus 4R, and the other side of the equation we have X square. So according to equation number 1, we found out that X square equals to R square minus 4R. Then we focused at this point T, that is the touching point of the semicircle and the circle, which is also the point of tendency of the semicircle and the circle. Actually, the circle and the semicircle have an external arch between them at point T. That is to say, they are touching each other externally at point T. Okay? And whenever you have two circular shapes that have an external notch between them, then the straight line that joins their centers together must pass through their touching point. Repeat again, whenever you have two circular shapes that have an external notch between them, then the straight line that joins their centers together must pass through their touching point. In this case, point P is the center of the circle, point Q is the center of the quarter, point P is the center of the circle, and point P is the center of the semicircle. And the straight line that joins their centers together is the straight line QP. And according to the rule that I mentioned, the straight line QP must pass through point D, that is their touching point. That is to say, QTP is one straight line. Okay, you can write here that QTP is one straight line, or here we can also say that the 3 points Q, T, and P, they are all located on the same straight line. Okay, so if QTP is a straight line, then QP is also a straight line, and QP is a straight line. So what is the length of the straight line QP? First of all, we know that QP equals to QT plus TP. Repeat again. QP equals to QT plus TP. So here, point Q is the center of the semicircle. Point T is the point on the semicircle itself. That is to say, QT is the radius of the semicircle, that is equal to 2 units. Likewise here, point P is the center of the circle. Point T is the point of the circle itself. Therefore, TP is the radius of this circle, that is also equal to 2 units. Okay, so here we found out that we know that QP equals to QT plus TP. We just right now found out that QT equals to 2 units and TP also equals to 2 units. Therefore, QP equals to 2 plus 2, that is 4. So we found out that the length of the straight line QP equals to 4 units. Then what is here? Point Q is the center of the semicircle, point B is the point of the semicircle itself, therefore BQ is the radius of this semicircle, that is equal to 2 units. And what is the length of line segment QL? From the drawing, it is very easy to see that QL equals to BO minus BQ minus LO. I repeat again, QL equals to BO minus BQ minus LO. Repeat again, QL equals to BO, that is the radius of the quarter circle, minus BQ, that is equal to 2 units, minus LO, that is also equal to 2 units. So in conclusion, we found out that QL equals to BO, that is the radius of the quarter circle, that is equal to capital R, minus BQ, that is 2, minus LO, that is also 2. So in conclusion, we found out that QL equals to capital R minus 2 minus 2, capital R minus 2 minus 2 equals to capital R minus 4. So in conclusion, we found out that QL equals to capital R minus 4. Then I copied the right triangle QLP in a new page and we implemented the Pythagoras theorem on this triangle QLP. So this is the right triangle QLP that I copied from the original drawing. We just right now found out that QL equals to capital R minus 4, LP equals to X, and we have only found out that the length of the hypotenuse QP equals to 4 units. Then we implemented the Pythagoras theorem on this triangle QLP. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The square of the hypotenuse is QP square, and it is equal to the sum of the squares of the perpendiculars, that is to say, it is equal to QL square plus LP square. So, according to the Pythagoras theorem in equation number 2, QP square equals to QL square plus LP square. QP equals to capital R minus 4, therefore QP square equals to, no, here QP equals to 4, therefore QP square equals to 4 squared, that is 16, and it is equal to QL square. QL equals to capital R minus 4, therefore QL square equals to capital R minus 4 square, plus LP square. LP equals to X, so LP square equals to X square. So in conclusion, found out that according to equation number 2, 16 equals to capital R minus 4 square plus X square. So here 16 equals to, we open the brackets on this side of the equation, so we got here that 16 equals to capital R minus 4 square, capital R minus 4 square equals to R square, plus 4 squared, that is 16, minus 2 times R times 4, that is minus 8R, plus X squared. So here we have 16 on both sides of equation number 2, so 16 will get cancelled, and after we cancel 16, in this side of the equation nothing is left, so we have 0, that is equal to capital R minus 8R plus X squared. Here we added 8R to this equation, equation number 2, and we got that 0 plus 8R is 8R, and it is equal to R squared, 8R minus 8R is 0, plus X squared. So in conclusion, we found out that according to equation number 2, 8R equals to R squared plus X squared. Here we added R squared to this equation number 2. We actually subtracted R squared from this equation number 2, and we got that 8R minus R squared equals to X squared. Here we added 4R to this equation number 2, and I found out that actually here we have 8R equals to R squared plus X squared. After we subtract R squared from this equation number 2, we got that 8R minus R squared equals to X squared. So according to equation number 2, we found out that X squared equals to 8R minus R squared, while according to equation number 1, we have already found out that X squared equals to R squared minus 4R. So we have two different expressions for R squared. Therefore, we created equation number 3 that states that X squared according to equation number 1 must be equal to X squared according to equation number 2. So X squared according to equation number 1 is equal to capital R minus 4R, while X squared according to equation number 2 is equal to 8R minus R squared. So, and those two expressions must be equal to each other. So here we added R squared to this equation number 3, and found out that R squared plus R squared is 2R squared minus 4R equals to 8R. Here we added 4R to this equation number 3, and found out that 2R squared minus 4R plus 4R is 0, and 8R plus 4R is 12R. So in conclusion, we found out that according to equation number 3, 2R squared equals to 12R. Here we divided this equation number 3 by 2, and we found out that 2R squared over 2 is R squared, and 12R over 2 is 6R. So in conclusion, we found out that according to equation number 3, R squared equals to 6R. Here we subtracted 6R from this equation number 3, and found out that R squared minus 6R equals to 0. Then we took out the common factor out of these expressions, and so here R is a common factor. So what is left from R squared after we took from it R is a common factor. What is left is actually R. And what is left from minus 6r over 32 commit r is a common factor. What is left is actually minus 6. So in conclusion, we found out that r times r minus 6 equals to 0. So here we will have two solutions that are possible for r. The first solution is r equals to 0, but because of the fact that r is the length of the radius of the quarter circle, r is select, it must be a positive number, it can never be equal to 0. So we cancel this solution and we left only with the second solution, that r minus 6 equals to 0. We added 6 to this equation and found out that r, the radius of the quarter circle, equals to 6 units. Therefore, the r of the quarter circle will be equal to the r of the circle over 4, that is to say, it will be equal to pi r square over 4. And what is the value of the shaded area? The value of the shaded area will be equal to the area of the quarter circle minus the area of the circle minus the area of the semicircle. I'll repeat again. The value of the shaded area equals to the area of the quarter circle minus the area of the circle minus the area of the semicircle. So the area of the quarter circle equals to the area of the circle over 4, that is to say it is equal to pi r square over 4 and r equals to 6. The area of the circle equals to pi r square and r equals to 2, therefore it is pi 2 square, and the area of the semicircle equals to pi r square over 2 and r equals to 2, so it is pi 2 square over 2. So here the area of the quarter circle is pi r square over 4 and r equals to 6, therefore r square is 6 squared, that is 36. So in total this expression equals to 36 pi over 4. This is the area of the quarter circle minus the area of the circle, that is pi 2 squared. 2 squared is 4. So in total this expression equals to 4 pi minus the area of the semicircle, that is pi 2 squared over 2. 2 squared is 4 and 4 over 2 is 2. So in total the area of the semicircle is 2 pi. So in conclusion, we found out that the shaded area equals to 36 pi over 4 minus 4 pi minus 2 pi. 36 over 4 is 9, so in total this expression equals to 9 pi, that is the area of the quarter circle, minus 4 pi, that is the area of the circle, minus 2 pi, that is the area of the semicircle. So 9 pi minus 4 pi is 5 pi, and 5 pi minus 2 pi is 3 pi. So in conclusion, we found out that the shaded area equals to either 3 pi square units, or in terms of numbers, it is equal to 9.42 square units. I'll repeat again. The value of this shaded area equals to either 3 pi square units, or in terms of numbers, it is equal to 9.42 square units. Okay? Thank you very much.